Welcome to lecture number 7 for ECE 341 Random Processes Z-Transforms. Now, where we are in this course is as follows. If you go to Bison Academy and click on 341, here's the syllabus for the course. What we've done previously is calculate probabilities using combinatorics and enumeration. We're going to now go into discrete probability functions, such as a coin flip, binomial distribution, rolling a 6-sided die, numbers are 1 through 6. Roll a 6-sided die until I get a 1. It could be 1 roll, 2 rolls, 3 rolls, and so on. Those are discrete probability distributions. To analyze these, we need mathematics that can handle discrete events. That's Z-transforms. So we're going to be looking at Z-transforms for the next 5 or 6 lectures. Now, Z-transforms are used in several courses. These are the courses you need to graduate in electrical computer engineering. Now, some of these use Laplace transforms. Laplace transforms are designed for analog systems, differential equations. So here we use Laplace transforms in Math 165, 166. Courses that deal with continuous systems, Circuits 1, Circuits 2, electronics uses Laplace transforms. Let's see what else. Control systems, other courses. Those all use Laplace transforms. Now, some courses use discrete events, like rolling dice. Those will use Z-transforms. So Z-transforms are used in embedded systems. If I have a computer program, it executes the program once every time I call the subroutines. That's a discrete event. That's Z-transform. Those used in signals and systems, Z-transforms, and also used here in random processes. So you're going to be using Laplace transforms and Z-transforms quite a few times over during your time in electrical computer engineering. Typically, people see Laplace transforms first. You'll be introduced to Laplace transforms in Circuits 1, Calc 1, Calc 2, courses like that. So we're going to have a kind of a brief summary of Laplace transforms, Z-transforms in this course. Now, you may have seen Laplace transforms already. Now, Laplace transforms are tools which help with the analysis of differential equations, like Math 266. They help with analyzing resistor, inductor, capacitor circuits, RLC circuits, with analog inputs. You do that in Circuits 1, Circuits 2. And they help with analysis of continuous probability density functions later on this semester in this course, 341. Now, the basic assumption behind Laplace transforms is that all functions are in the form of e to the st. What that does is when I take the derivative, I get s e to the st, or s times y. So with Laplace transforms, I can interpret s to mean the derivative. So s times y means the derivative of y. What Laplace transforms do is they turn differential equations into algebraic equations in S, and the assumption is that algebra is easier than calculus. So for example, anytime you have a system described by a differential equation, you typically use Laplace transforms. What that does, that converts your differential equation into algebraic equation in S. So for example, suppose I have this differential equation, and here's my input. Find y of t. Well, that's actually a hard function to solve. You'll do that in Calc 1. It's about a 30-minute problem. With Laplace transforms, it's actually much easier. I let s mean derivative, so here's the second derivative of y. First derivative of y, just y. First derivative of x, and x. Do some algebra, rearrange it, I can get y in terms of x. So the numerator polynomial is what multiplies by x. The denominator polynomial multiplies by y. So this is kind of the gain from x to y. If I have a very specific input, I take the Laplace transform of it. This is the Laplace transform of 3 e to the minus 2t. We'll cover that later. You'll cover that later in your classes. And what I wind up with is the Laplace transform for y. I can then take the inverse Laplace transform to find y of t. So that is kind of Laplace transform. It makes a hard problem to solve, a problem that takes about 30 minutes using techniques in Calc 2, Calc 3, and turns it into an algebra problem. This takes you maybe 5 minutes to solve, probably less. So anytime I'm dealing with continuous functions, differential equations, I use Laplace transforms. Another nice thing that Laplace transforms do is the solution to this is I take the impulse response of my filter, h of t, convolve it with the input. The convolution produces the output. Another property of Laplace transforms is they turn convolution into multiplications. And convolution is something we'll talk about in this course as well. So if you haven't seen it, you will see it again soon. This course and several other courses. What this means is that anytime you need to convolve continuous functions, something that's kind of painful to do, if I switch to the frequency domain, Laplace transforms, I can solve using multiplication. And multiplication is way easier than convolution. You'll see that when you take signals and systems. Basically, Laplace transforms are used in many different courses. In most of these courses that you'll see, the Laplace transform is called that. Laplace transforms. The oddity is right here. In random processes, in statistics, Laplace transforms are called moment-generating functions. It's the same thing with a different name, so I'm going to be using Laplace transforms. That's what we call it for most of the ECE curriculum. And this is designed for continuous systems described by differential equations. It's designed for continuous probability density functions, stuff that we'll be covering later in this course when we'll be using Laplace transforms. So that's kind of an overview of Laplace. We're going to be looking here immediately at z-transforms. So z-transforms are similar to Laplace transforms. They're tools that help analyze difference equations. That's different than a difference equation. A difference equation is when you have something like y of k plus 1 is a function of y of k and x of k. These are discrete time systems. Z-transforms help with analyzing circuits where the inputs are digital, such as a microprocessor. I'm going to output a voltage and update it every 10 milliseconds, every time I go through the loop. That's where we use Z-transforms. They also help in analyzing probability functions with the discrete events, like rolling a die. The value can be discrete numbers 1 through 6, or the number of rolls until I get a 1. That's 1 roll, 2 rolls, 3 rolls. Those are discrete numbers. In those situations, we also use Z-transforms. Now, the basic assumption behind Z-transforms is that all functions are in the form of z to the k. What that does is if I make this a difference equation and I move forward in time, y of k plus 1, that becomes z to the k plus 1, or z times y to the k, y of k. So zy is an operator just like sy. Sy means the derivative of y. Zy means the next value of y. One sample in the future. What z-transforms do is similar to what Laplace transforms do, only now it's difference equations. What the z-transform does, it converts difference equations that look like this, into algebraic equations in z. For example, if I have this difference equation, zy means next value, so 2 samples in the future becomes z squared y, 1 sample in the future, zy, current y, next value of x is zx, current x is x. Do some algebra, pull out the y's, solve for y in terms of x. I get this. Here's my transfer function. This is the gain relating x to y, but it's a function of z. So this means a discrete time system versus s, which means a continuous time system. Or z means a difference equation, s means a differential equation. Now, if you're dealing with a system that's continuous, you typically use Laplace transforms. That could be continuous in time or probability. Time is what you do in signals and systems. Probability is what you do in this class, in statistics. If you're dealing with discrete functions discrete function that's in time or in probability, then you use z-transforms. So in this lecture, we're going to talk about the z-transform, some background on it, some of the properties, and how to use it. Now the definition of a z-transform is the sum of x sub n z to the minus n. What that means is if I have a function that looks something like this at k equals 0, 1, 2, 3, if this is the function, say 3, 1, 3, 2, it's kind of a definition. Then the z-transform would just be 3 at k equals 0 plus 1 delayed by 1 plus 2, actually 3 delayed by 2 plus 2 delayed by 3. So that's the z-transform of this function. That's the definition of it. A property of z-transforms is that it's linear. What linear means is the z-transform of ax plus by is a times the z-transform of x plus b times the z-transform of y. And you can see that by plugging it in. If I have a function of axn plus by of n, that's the values times z to the minus n, multiply through, distribute the z's, pull out the a's, pull out the b. This is the z-transform of x. This is the z-transform of y. So the z-transform of ax plus by is a times the z-transform of x plus b times the z-transform of y. Z-transforms are linear. Time shift. If I delay something by k samples, that's the same as multiplying by z to the minus k. And I can check that. X of n minus k is, by definition, x of n minus k times z to the n. Do a change in variable. Let m be n minus k, so that's x of n. N becomes m plus k. Distribute this, that's z to the minus m, z to the minus k. Z to the minus k, I can pull outside. There's no m's in it. So it's z to the minus k times this. That's just the z-transform of x. So delaying a system by k samples is the same as multiplying by z to the minus k. That's a delay. 1 over z is a delay of 1 sample. We'll be using that later. Convolution. Here's the biggie. If I convolve in the time domain, I multiply in the z domain. And to see that, convolution would be the sum of x sub k, y of n minus k, sum for all k's. That's the sum. We're plugging it in. This is the z-transform of it. What I can do, change the order of summations, switch these two. Since x isn't a function of n, pull the x outside. Do a change in variable like we did before. M is n minus k, so here is y sub m, z to the m plus k, the minus sign. Do this as z to the minus m times z to the minus k. Pull the k's outside here since it's not a function of n. That gives you the z-transform of x times z-transform of y. So anytime you're dealing with convolution, I can turn that into multiplication by going to the z-plane. We'll be doing that quite a bit. If you want to convert from the z-plane to the time domain, one way to do that is use a table. So here's a table of z-transforms. This is pretty much all we're going to use in this course. You can go to the CRC Handbook of Math and Physics, and they've got about 30 pages of z-transforms. This is really all we need. This and partial fraction expansion will let us find most of the terms. To prove the table entries, there's a couple ways to do that. First, let's start with the delta function. Delta function is 1 at k equals 0, 0 elsewhere. kind of by definition, that means the z transform is 1 plus 0 over z plus 0 over 2z over z squared, 0 over z cubed, and so on. The z transform is just 1. That's basically a definition. Again, that's the delta function in the z-plane, 1 at k equals 0. A unit step. Now, if I have a unit step that's 1 or k equals 1, k equals 0 to infinity, 0 otherwise, if I delay this, 1 over z is delay, so that takes your function, delays it by 1. Now subtract. 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 0 is 0, 1 minus 1 is 0. I get this. This is a delta function. I like delta functions because the z transform is 1. Now solve. I divide by 1 minus 1 over z, clear the fraction, times z over z, gives you z over z minus 1. This is the z transform of a step. And that's what a step looks like. It's 1 for k equals 0 on up. If I have a decaying exponential, starts at 1, goes to a squared, a cubed, and so on. That has a z transform of z over z minus a. To see that, let's start with a decaying exponential. This is 1 at k equals 0, a squared, a cubed, a to the fourth, and so on. Let's take this function and delay it by 1. And when I delay it, I'm going to delay it and multiply by a. So here's the a divided by z. That's a delayed by 1. Now subtract. When I subtract, I get 0, 0, 0, except for here. That's delta function. So this is equal to 1. Solving for x. Replace it for common denominator. So that's z minus a over z times x equals 1. Solve for x. X equals z over z minus a. That's the Laplace transform of a decaying exponential. So that's kind of the table entries. With that, we can solve different problems. Like suppose I have this problem. Y is a function of x, and the gain is in terms of z. Suppose x is a unit step. In that case, I take x, replace with the z transform of the unit step. That's z over z minus 1. That's y of z. That's the z transform at the output. If I want to find y of k, I need to take the inverse z transform. Now this is not in my table. Some tables have all these terms, but there's just too many degrees of freedom. One way around that is use partial fractions. Now if you notice in this table, all the terms had a z in the numerator. There's all the z's. So it would be nice if I had a z in the numerator when I did a partial fraction expansion. So that's what I'll do. I'll take my function here, pull out a z, leave it outside. So when I do the partial fraction expansion, I can multiply through by z, and I still have that z in the numerator. So that's kind of the trick. With partial fractions, I know there are going to be three terms: something over z minus 1, something over z minus 0.9, something over z minus 0.5. To find the terms, use the cover-up method. To find the term over z minus 1, cover up this term, analyze at z equals 1, I get 4. To get the term over 0.9, I cover up the z minus 0.9 term. Plug in z is plus 0.9. Do that analysis, I get minus 4. To get the z minus 0.5, cover up this term, analyze the inside at z as plus 0.5, I get 0.5. So here's your partial fraction expansion. Now multiply through by z. Take the inverse z transform. So this becomes 4 times 1 to the k minus 4.5 times 0.9 to the k plus 0.5 times 0.5 to the k. For k positive, you can either say k equals 0 or times u of k. Either one's the same. And if I plot it, here is what y of k looks like. This works with complex poles. Suppose I have the following system, find the step response. Again, what I do is replace x with a z transform, that's z over z minus 1. This isn't in my table, so I'm going to pull out a z, do partial fraction expansion, and at the answer will be something over z minus 1, something over z minus 0.9 at 10 degrees, something over z minus 0.9 at minus 10 degrees. Do partial fractions, analyze this as z equals plus 1, and I get 5.355. Analyze this part at z equals 0.9 at 10 degrees, and I get a complex number. Do the last term, I'll get the complex conjugate. Now using the table, find the inverse z transform. This is just 5.335 times u of k. This is double that. That's from Euler's identity, 4.958. The amplitude of the pole is your 0.9 of the k. The angle is the frequency, cosine of 10 degrees times k. So one cycle is 360 degrees, one cycle is 36 k's. This repeats every 36 k's. And it turns out the angle is the term over the minus degrees, at minus 153 degrees. So there's y of k. Now there's a trick. If the numerator doesn't have a z term, I need that for the inverse z transform. That's not a problem. What I can do is multiply by z, pull the z outside, do the partial fraction expansion, multiply through by z, so here's the z transform of z times y. Now this, I can take the partial fraction, or I can take the inverse z transform, that's just 4 minus 5 times 0.9 of the k, plus 1 times 0.5 of the k. That's z times y. Divide by z. Divide by z is a delay by 1. So replace k with k minus 1. Here's delay by 1. And here's your answer. Equivalently, I could take that 0.1 minus 1, bring it outside, and get this answer. Either one's correct. Now sometimes you have repeated poles. If you have repeated poles, same procedure. With repeated poles, I'm going to have something over z minus 1, something over z minus 0.9 squared, and there'll be a third term. You can have something over z minus 0.9. So keep on reducing the powers until I get to 1 and stop. So there'll actually be 3 terms in partial fraction expansion here. A and b I can find using the cover-up method. Plug in z equals 1, analyze, I get a. A is 40. If I cover up this term and plug in z equals plus 1, I get b. To find c, a couple ways to do that. What I do is place this over a common denominator and match the numerators. So to put this over a common denominator, a over z minus 1 has to be multiplied by z minus 0.9 squared, top and bottom. B has to be multiplied by z minus 1, top and bottom. And the c has to be multiplied by z minus 1, z minus 0.9. I now have a common denominator. The numerators all add up. When I do that, I should get 0.2 times z plus 1. All 3 terms have to match. If I match the square term, this is 0 z squared. Is equal to a times z squared plus c times z squared. So a plus c equals 0, c is minus a. Here's the partial fraction expansion. Now, I don't have a z, so what I'll do is multiply top and bottom, or both sides by z. Take the inverse z transform. Now divide by z, which means delay by 1. That's one solution. Second solution is to note that the denominator is order 3, numerator is order 1. To make them both third order, multiply both sides by z squared. Now numerator's third order, denominator's third order. The difference in order is the delay in the system. So here there's no delay in the system. This turns on at k equals 0. Take the E inverse Z transform, pull out a Z, do partial fraction expansion, solve for A, B, and C, multiply through by Z. Now we can take the inverse Z transform. That's 40 minus 3.42k times 0.9 to the k minus 39 times 0.9 to the k. And that's Z squared x. Divide through by Z squared to get x of k. Dividing by Z squared means delay by 2. So k becomes k minus 2 everywhere. Here is another version of the answer. Now both versions are correct. It's kind of a matter of preference. Finally, let's do another example of Z transforms. This is something you do in business quite often. It's time value of money. If I want to borrow $100,000 for 10 years, what are my monthly payments? Well, what I would do is set up the equation for this. This is how much I owe next month. Next month is how much I owe this month, plus 6% divided by 12, 1.005, minus my monthly payments, plus the initial loan, $100,000. The initial loan only happens once. That's my delta function. This turns on at k equals 0 and 0 elsewhere. I borrow $100,000 once and never again. Now take the Z transform. X of k plus 1 is zx of k. Here's x. This is a unit step that turns on at k equals 1. When you borrow money, you don't pay money back right away. You wait a month, then you pay money the first month up through the 120th month. That's 10 years, 120 payments. And borrow money at k equals 0. That's my delta Laplace transform, or Z transform of delta function is 1. Now, let's put this over a common denominator and solve for x. I wind up, this is the Z transform of x. Do partial fraction expansion for p. Multiply through by z. Take the inverse Z transform, and here's zx, and here's x of k. That's the equation for how much money you owe at each month. Now to solve for your monthly payment, I want to have when at x of k is 120, I owe 0 money, everything's paid off. At that point the loan is paid off, I can clear my books. So take that previous equation, plug in k equals 120, x of 120 should be 0. That works out to, analyze this term, 181,034 minus 162.09p. Solve for p. P is 117. So if I were to borrow $100,000 over 10 years, that's my monthly payment. Now this is something you do in business. In business, this is a common problem. They're really doing Z transforms. They don't call it Z transforms, but that's really what they're doing. So that's kind of a summary of Z transforms. So Z transforms are similar to Laplace transforms, but they deal with discrete time systems. They also deal with discrete time probability functions. Anytime you're dealing with difference equations, like y of k plus 1 is a function of y of k, anytime you're dealing with discrete probability functions, you'll find the Z transforms are useful. Now in signals and systems, the Z transform represents a signal, and its value at k equals 0 could be anything. In random processes, x of z represents a probability density function, and all probabilities have a probability between 0 and 1. So in this class, it's going to be slightly different. In signals, the Z transform could be anything. In this class, it has to be a valid probability, meaning all numbers have to be between 0 and 1. In addition, Z has a different name. In signals and systems, the Z transform is called Z transform. In this class, it's called the moment generating function. Different name, but same thing. So that's kind of a background on Z transforms. We'll then be using Z transforms for the next couple lectures to analyze discrete probability functions, including coin flips, flipping the coin n times, rolling n dice until I get a 1, rolling n dice until I get 2 1s. Those will all be discrete probability functions. That's lecture number 7 for ECE 341, random processes, Z transforms.